Hello, everybody. Welcome to our Thermal Management of Power Semiconductors in Your Design webinar hosted by Avnet, Laird, Siemens, and Toshiba. I'd like to welcome you all, and hopefully you're having a great afternoon and good morning for those on the West Coast. We'll be taking written questions at the end of the session. You can put those in the question part section. You can click on that and ask any questions you want. We'll be answering all those at the end. Hosts for today are Dave Winter from Sachs and myself, Mike Nicolak from Electrosource. And we have three presenters, Jim Latham from Laird, Jurgis Astrokis from Toshiba, and Andres Vasvanai from Siemens. Just to quickly go through the agenda, we're going to discuss trends in power electronics and thermal management challenges, TIM material types and suitable applications, power device packaging and thermal design considerations, applying thermal transient testing technology, power control module, TIM material comparison study, ensuring manufacturing thermal quality, and discrete component thermal quality testing study. And then finally, we'll wrap up with just a one-page summary and then a question and answer session. I'd now like to introduce you to Jim Latham from Laird.
Thanks, Michael. Hi, I'm Jim Latham. I'm a product manager for thermal interface materials at Laird, and I'm going to be presenting today our thermal interface material portfolio, focusing on our newer products and how they fit into the applications and challenges that we're facing today. But before I do that, I'm going to talk a little bit about some high-level trends that are occurring today in the electronics industry. The electronics industry, as far back as I can remember, and I've been involved in thermal interface materials on and off for the past 30 years. The mantra has been, electronics are getting more powerful and more condensed, smaller packages. And, that's just a formula for, thermal issues that need to be addressed. And trends today, we see the high performance computing, all of the data that, are being generated by all the social media platforms and all of the gaming and virtual reality based computing that is needed. And then there's the high frequency conductivity. Again, everybody wants to get their data out of the cloud instantaneously, and there's a big push to get 5G up and running. Advanced mobility, which is drive-by-wire, it's EV, it's autonomous driving, and we just about have home theaters in our cars now. It's pretty amazing, and that's driving a lot of increased semiconductors in the automobile industry. And finally, another big area is energy efficiency, where we can see the focus on white goods and everything in the home being more energy efficient, and all of the controls that go with being able to turn those things in your household and really even in manufacturing, all off and on from like a touch of a button remotely. And as we then kind of drill down a little farther and look at the power market and what's going on there, we can see it's slated to grow quite aggressively over the next 4 or 5 years as well. And this is really driven mainly by the automotive industry. And we can see that, the automotive industry is, again, slated to like double the amount of power semiconductors it's going to use in the coming years, both driven by discretes and modules. with the really big chunk of this being the emphasis on EV, electric vehicles. We also can see that motor drives in the industrial market segment are slated to grow, while portable wireless and computing storage stay about the same. Well, we can't really talk about what's going on in power semiconductors without talking about, wide band gap. That's silicon carbide and gallium nitride. There are huge advantages to moving to these semiconductor platforms. Obviously, silicon has been the mainstay and is a cheaper, less, more cost-efficient platform today. But as we move to these other semiconductors, their prices will come down, especially when we look at all of the benefits that we get from them, which is shown by the spider graph on the left. And then looking at kind of where these new materials are going to play, you can see how they overlay the existing silicon applications. So we really need to focus, since the big driver of the growth over the next few years is the automotive industry. I think as we look at, what are the requirements for power semiconductors and even the thermal interface materials that go along with them, we have to look at what's going on in the automotive market. And again, on the left here, you can see all of the electronic systems that require semiconductors, quite a few, and growing. And then on the right, we can kind of compare the constraints or expectations of semiconductors in the consumer market versus the automotive market. And you can see that the automotive market has, a lot more stringent requirements in operating range, life expectancy, failure rates, and so on. So it's going to be a driving consideration in designing. The other trend that we see is that, we're pushing more power out of these semiconductors and trying not to increase the volume, right? We want to keep everything small. And to do that, we really have to look at more intricate cooling solutions, which you can see here: integrated heat sinks, dual-sided cooling, and even the adaptation of liquid cooling into some of these. So how do TIMs play into this? Well, if we just look at IGBT stack up from the IBG chip to the heatsink, the largest thermal resistance component in getting the heat moved from one place from the IGB chip to the heatsink is the thermal interface material. So there's still an strong emphasis on, continually improving the thermal performance of thermal interface materials. So if we look at the overall thermal interface material market, we can see that it's growing at a nice clip as well, which should be expected since the electronic market is growing as well. And if we look at the power section of this in blue, it's really growing faster than what we indicated earlier as the overall power market. And I think that's due to the fact that a lot more of the existing applications today are going to need thermal management. So the need for thermal management in power electronics is really outpacing the growth in the power market itself. All right, getting into more details specifically on thermal interface materials, I like to divide them into 4 classifications, and we'll dive into each of these in a little more detail as we go through. They are thermally conductive insulators, gap fillers, which are both pads and dispensables, tapes and adhesives, and then finally high performance grease and phase change materials. And the first three have kind of dual purposes. The thermal material in the first one needs to be an insulator. In the second one, it needs to fill, a large gap. And the third one, outside of being a thermal transfer medium, it has to provide a mechanical attachment. And all of those are constraints on the thermal performance. And when we remove all of those constraints and say, look, thermal performance is the only thing we care about, you can see that we can move into this high performance group of greases and phase change, and the performance level really jumps close to 10x, which is indicated by the graphs on the right. So taking a look at each of these product families, thermally conductive insulators, they are what they say they are, right? They're insulators. In designing insulators, they really need to be rugged. They need to be abrasive resistance, have high tensile and tear, strength, because of the high pressures and forces involved in a lot of the power electronics applications. That means that the materials need to have they need to be harder than general. And in that case, it's harder to get the thermal performance that you can get out of something like a grease or a phase change. So as we look at the Laird portfolio for thermally conductive insulators, we have a wide range of different constructions. We have PE and PI films coated with various phase change materials. The PE and PI films providing the electrical isolation. And then we have the more traditional ceramic-filled silicon elastomers, which is kind of the traditional thermally conductive insulator pad. And then finally, at the end, we have kind of a dual purpose insulator adhesive film. It's an epoxy film that can be used to bond the power component down to the heatsink. And again, we see a need to drive that product family to a higher temperature range. And again, this is driven by the automotive market. Going from the TNC4 to the TNC5, we're looking to increase the operating range to 200 degrees C and have an RTI rating of 150 degrees C. Next product family is the gap fillers. Gap fillers replace air for the most part in large gaps. So and they heat or they cool multiple components to one heatsink. That's the general application, which you can see in the bottom here, where you have different thickness gap filler pads cooling different size components to a common heatsink. It's a very common application for gap fillers. So we look at our gap filler product family. Laird has a wide range of gap fillers. We're very strong in the gap filler market. This is just a small representation of our gap filler products. And I have two new products listed at the end. There are T-Flex SF10 and our HP34. Both of these are, increases in thermal conductivity. With the SF10, we've broken into double digits, and with the HP34, we've really made a big jump in performance. This graph kind of shows our product portfolio in a couple of ways. The bars are thermal conductivity, and the line graph is hardness. So you can see we have a varying range of thermal conductivity and hardnesses. The green bars are non-silicone or silicone-free products. We have a high deflection series, and we also can provide gap fillers with an insulating layer, which is generally some type of a PE or PI film. Again, if you look at what's new down at the end, you can see where the SF10 and the HP34 fit in. And I think this this graph does a really good job of showing, you know, the huge jump we've made going to the HP34. All right, the other section, which is really growing even at a faster rate than the overall TIM market in general, is the gap filler dispensables. This has two big advantages. It's the automation. People can automatically put down different amounts on different components on a board automatically with a dispensing system, like shown in the picture below. And the other compelling advantage over dispensable over a pad is the low stress on components. And that's indicated in the graph. There is a certain amount of assembly pressure that if you assemble something quickly with a pad, you're going to get a spike in the pressure where you won't get with a dispensable, and those spikes in pressure potentially can damage the components. So in those type of more delicate applications, people will look to dispensables. Dispensables come in both 1-part and 2-part. 1-part dispensable is, you know, for the most part pre-cured. It stays putty-like for the life of the product. It's, you know, it's easily dispensed because it's a 1-part system. It's easy to clean up. You know, it is a 2-part system. It requires a, you know, mixing through some type of static mixer right at the head. It does need to be cured as well. But what it does provide is higher reliability than you would get from a 1-part, since it cures. It is, you know, forms especially at higher gap thicknesses, a much more reliable joint. And, you know, for the automotive market, which we've already shown, you know, the reliability and product lifetime that's required, they definitely lean to 2 parts over 1 part. This is a chart of our dispensable gap fillers. Again, in orange are our new products, and we continue to move up the thermal conductivity ladder. We've recently introduced the 2-part. The T-Flex CR numbers are 2 parts, where these are 1 part. So we've just introduced a CR607, and it's a 6-watt 2-part dispensable. We're very imminently launching CA900 and T-Putty 900, which are even higher thermal conductivity yet. And you can see that on all 3 of these, the operating range is 200 degrees C, which make them very, very good candidates for the automotive market as well. Finally, we have the high performance product family. Again, this is where we're going to cool the most critical components. They're generally used in a 1-to-1 situation where there's 1 heatsink to 1 component, in a constant pressure application where there's some type of spring mechanism holding the heatsink to the component. In this application, then the grease or the phase change can go to a minimum bond line, whereby reducing the thermal resistance. And we see applications for these materials in CPUs and GPUs and IGBT modules. You can see from the pictures on the right. Looking at the Laird portfolio, again, we've got a wide range of different phase change materials and greases, and focusing on the new ones again in orange. The 7000, which just released, has an operating range of 150 C and you know, 7.5 watts per meter K thermal conductivity, which is like leading edge performance. All right, looking at our overall roadmap, we've touched on a few of these as we've gone through the presentation. The gray and blue products have been released or are very imminently going to be released, like within the next, I would say, 3 to 6 months, and the green ones kind of longer term. And you can see from the arrows that the general trend is, in all of these products is increased thermal conductivity. We're looking forward to getting these new ones out, in the next year or so. All right, final slide is just some other materials that I want to touch on. We do have a CoolZorb line. This is an elastomeric product that can both be used as a thermal gasket and an EMI absorber. So it's a combination product, and we have a range of thermal conductivities and absorption characteristics that you could use in your applications. The middle illustration and product is our TLAM prepreg system. We manufacture a thermally conductive prepreg that can be used to make circuit boards, which then gives you an inherently thermally conductive circuit board, where now you may be able to reduce hardware required on top of the component because you have thermal dissipation through the board. You can use a metal substrate as a backer, aluminum or copper as a heatsink on the backside of the board, if your design permits that. And this prepreg has a thermal conductivity about 3, which puts it about 10 times the thermal performance of typical FR4. Finally, we have our GOF, which is a graphite over foam product. We are using the high thermal conductivity in the XY direction of synthetic graphite to transfer the heat around a foam core. And this foam core, provides, very low stress on components. It has great spring back, and is great for applications where you've got large gaps. All right. Well, thank you. Thank you for listening to my presentation, and I will now pass this on over to Jurgis, who's going to talk about power device packaging and thermal design considerations. Thanks.
Hello, everyone. My name is Jurgis Ostrauskas. I'm Director for Technology Development on Toshiba. Power electronics, trends, driving design considerations, they also dictating semiconductor suppliers to keep increasing performance, efficiency of power semiconductors, packaging technologies. So we'll talk about Toshiba's power dual side packages, ceramic substrates. Toshiba's focus on power devices for industrial, consumer, automotive applications, power range from 1 amp to 1000 amps up to 3300 volts. They're offering discrete transistors, MOSFETs, low voltage MOSFETs, high voltage planar, super junction, high voltage MOSFET, silicon carbide MOSFET, silicon carbide Schottky diodes. We have GaN devices as well. Also integrated small power modules for 3-phase motor drives, also modules for very high power industrial applications. We have all industry standard packages, surface mount 5x6, dual side cooling 5x6, for example, is being used by Siemens for today during the webinar for thermal testing evaluation. Also our super junction DTMOS 6th generation super range high voltage MOSFET as well. Addressing heat dissipation aspects by developing new power devices and packaging technologies. So higher efficiency power transistor technologies contribute to lower power loss. Lower RDSN gives lower conduction loss. Improved trade-off between RDSN and QG, Q switching, gate charge, or output charge, lower switching losses. Higher maximum junction temperature, 175 degrees C, smaller, higher RTH heatsink, lower cost heatsink can be used. lower thermal coefficient. Our technology for MOSFET has lower thermal coefficient and lower radiosan increase when the temperature rises to actual working temperatures. It gives lower power loss during the actual working temperature conditions. Packaging technology improvement. So we're not only focusing on the semiconductor improvement by itself, or packaging technology improvement. We're using copper connector, copper clip. It gives lower RTH junction to case. It also attributes to lower radiosan. Dual side cooling packages, again, lower RTH, better heat transfer. For our high power modules, we're using silicon carbide, silicon nitride ceramic substrates. It gives higher thermal conductivity. So the right design choices deliver improved thermal management of the power conversion system. So what can be done to minimize power device temperature, heatsink size, cost, simplify a cooling system, and improve heat dissipation? So the number one, the very first step is to minimize the amount of heat that has to be transferred from power device by using higher efficiency power devices. Silicon carbide and gallium nitride are coming into spotlight as materials for power semiconductors. These innovative power semiconductors are able to help designers make system more efficient, improve thermal management. Extracting heat from power device can be significantly enhanced by optimizing thermal management system and using higher performance substrates and thermal and isolation interface materials, innovative packaging. For low voltage FETs, Toshiba is using a copper connector clip. It gives us lower RTH junction to case, lower radiosan. Using dual side cooling packages that improve heat dissipation. To improve thermals on our silicon carbide high power module with the FETs, we're using silicon nitride ceramic substrates that give us higher thermal conductivity. So Toshiba low voltage MOSFETs, why Toshiba? So we are on the 10th generation high performance trench technology. We have leading industry leading class figure of merit, wide range of surface mount packages. So again, like efficiency is the key. We are leading in this area comparing to others. Process improvement. So also optimizing the structure of this MOSFET structure. There is instinctive parasitic snubber inside. Each MOSFET has it. So we are tweaking this snubber, and it helping us to minimize the spike. So it gives low voltage spike, lower EMI, higher reliability, easier to do the design. It helps designer. Copper connector. So there are other semiconductor manufacturers using copper connector. We're using wider connectors, larger connector. It gives us better thermals. So junction to top side, junction to bottom side, they are much lower comparing to others. Dual side cooling, we call it DSOP advanced package, has a metallic plate on top, and it helps to dissipate heat from the semiconductor, from the silicon, from the die to from the top side. And the thermal resistance of the dual side cooling device from the top side is by 45% lower comparing to single side cooling device. Also, this is like an example showing the heatsink can be attached on the single side cooling device, and the thermals are much worse because the heat is transferred through the mold, through the resin, and the RTH is much larger using dual side cooling device. And the junction to case, the bottom side injection to case, top sides are very similar, 0.93, 0.88 degrees C per watt. So it's a very sufficient, much more advanced comparing to single side cooling device. So those examples are showing how the dual side cooling device is mounted on the printed circuit board. So device is mounted on the board, and on the bottom side there is a copper. So the dual side cooling device dissipates the heat from the top side and to the bottom side as well. So those two pictures are showing the single side cooling device mounted on the board, and it dissipates heat from the package going through the board to the other side, to the copper. Where on the right side there is a dual side cooling device, and it dissipates heat to the bottom side and also to the top side and attach the heatsink. So we have done some thermal measurements in our lab. So, but this is like a real life example for like a single side cooling device, for example, has 103 degrees C case temperature. And switching from single side cooling device to dual side cooling device, and we put the same die in the single side package or the dual side cooling, but switching to dual side cooling device, it reduces temperature to 92 degrees. So already a significant improvement. attaching the heatsink on top decrease the temperature to 77 degrees. So in our lab, we have done testing, analyzing single-side cooling device, dual-side cooling with the heatsink, without the heatsink. But basically, the quick summary shows that single-side cooling device with the heatsink attached on top has 90 degrees temperature case, whereas the dual-side cooling device without the heatsink has 92 degrees C. So basically it tells that switching to dual side cooling device, it allows to eliminate the heatsink. Example of using dual side cooling devices, for example, is a printed circuit board with the multiple devices on it. It can be an example, a computer board, a multi-axis motor control, automotive controller board. So multiple dual side cooling devices in the board covered with one heatsink. So this shows the structure, how it has to be mounted. The dual side cooling device is subject to the printed circuit board. The heatsink is on top, and it has to be used insulation, thermal interface material, high viscosity material to distribute properly the force of the heatsink, the screws, if the screws are used, to distribute proper force to all those devices. Second slide is showing Toshiba is a motor control reference design board, evaluation board. We have developed this board for a electrical power tool customers. So basically this board is using Toshiba's microprocessor to drive the motor control portion. You can see 6 dual side cooling transistors. They are covered by copper clips on top. They're saturated, so working as a heatsink. So we're using TPWR 804 PL transistors. Those are 0.8 milliohm max radio sound transistors, 40 volt rated. The silicon limit is 340 amps for the devices. The package limit 150 amps. So you'll see the thermal testing is done by Siemens during the seminar. And this table is showing all our devices available in the dual side package. So again, we're taking the same die and we put them in the single side cooling device and in the dual side cooling device. We have devices offering from 30 volt to 250 volt, various current ratings, various radio sound levels. Silicon carbide devices, power module, ceramic substrate. So Toshiba, we have developed our silicon carbide technology. We are manufacturing silicon carbide SBD Schottky diodes, silicon carbide MOSFETs. So we have 650 volt diodes, 1200 volt diodes, 650s. They are coming in development right now. 1200 volt devices, already some of them in the mass production. We're offering them in several different packages. More devices coming this year and the next year as well. A few words about Toshiba's MOSFET technology. Why Toshiba? So why silicon carbide MOSFET from Toshiba? So one logical advantage from Toshiba is a much higher gate voltage threshold. Our typical voltage threshold is 5 volts. It's larger compared to other silicon carbide MOSFET suppliers, and it allows to use single polarity gate driver. So it doesn't have to be used negative voltage power supply to the gate driver. This unipolar gate driver can be used. And also where the voltage threshold is higher, it's easier to keep transistor off securely to avoid malfunction, avoid self turn on. Another one very interesting which is built-in SBD. So conventional silicon carbide MOSFET has instinctive body diode, but the diode, even it is silicon carbide MOSFET, the diode is not SBD diode, it's not Schottky, it has quite high voltage drop. So in order to overcome it, the separate die can be used or a separate external diode. Toshiba has implemented, we call it SBD built-in technology. So the diode is a part of the structure of the whole MOSFET. It's not a separate die. And it gives us forward voltage drop 1.35 volts. It's much lower compared to conventional MOSFETs, silicon carbide MOSFETs in the market. Also, we have wider VGSS rating for the gates. So our rating is minus 10 volts to 25 volts is the highest, the widest on the market. So this table is showing other players, how they're dealing with VTH and VGSS max. Toshiba full silicon carbide power module. So we are launching a silicon carbide module. It's a Hell bridge module, 2 transistors inside. So we're targeting high power applications, industrial applications. So we have first module, 3300 volts, 800 amps, again for industrial applications. And inside the module, as an insulated substrate, which is holding those dies, we're using silicon nitride substrate. So at Toshiba, we have a materials group, which is developing, we call it like a fine ceramics for electronics. So for automotive electrification, traction inverter, hybrid vehicles, electrical vehicles, smart grids, solid state transformers, solar inverters, also to produce lasers for optical communication. So it shows like one of our modules, and we're using silicon nitride substrate, ceramic, instead of aluminum oxide. So a few key parameters for silicon nitride substrate. So it's a higher mechanical strength, is much higher comparing to aluminum oxide, much higher thermal conductivity, higher reliability. Advantages of silicon nitride increase under delta temperature for thermal cycling testing. So high thermal cycle, more than 3000 cycles, minus 40 degree to 120 degree. And it's the best physical solution for silicon carbide and gallium nitride power modules. So this table shows main parameters for silicon nitride comparing to aluminum nitride and aluminum oxide. So the key parameter is conductivity is much higher compared to aluminum oxide. And the bending strength, fractional toughness is much higher. Its ability to use thinner isolation material, thinner ceramic, since it's much stronger, and it allows to even increase the thermal conductivity as well. Another one very important parameter is coefficient of thermal expansion. It's 2.6. It's very similar to silicon. So during like a thermal cycling, during the temperature variations, they're expanding, linearly expanding in the same rate. So it's much lower risk of getting malfunctioning. And so silicon nitride substrate delivers higher power density. So conventional design is using resin, aluminum oxide ceramics, and comparing to silicon nitride ceramics. So we can achieve either output power twice or size reduction by half or by 1/3. But basically the thermal resistance is lower, and we're using thicker copper plate and thin silicon nitride, higher thermal conductivity material. So again, it gives higher output power or actually downsizing the system. And that was the last slide. So thank you so much for your time. I'm hoping you will have, I will be using more Toshiba products. I want to transfer presentation to Andras from Siemens, and he will continue. Thank you.
Thank you very much, Jurgis. My name is András Vasvárnai. I'm a Global Business Development Manager for Siemens. And I'd like to show first an introductory slide about the group I'm working for. It's called Siemens Digital Industries Software, and there is a so-called Sim Center simulation and test portfolio, which contains thermal, structural integrity, acoustics, sound and vibration, electromagnetics, both high and low frequency, and contaminant related products. Most of these products work together in separate workflows, but today I like to focus on thermal management, mainly on test and a little bit simulation. So in relation to the thermal interface material and power semiconductor topics my colleagues just presented before me, when we try to characterize either a component or maybe a system or a subsystem, one of the most important things to understand is the thermal structure. So what are the thermal metrics from junction to ambient, maybe junction to case for a certain semiconductor device, and how the device is built up when it comes to the thermal resistance and thermal capacitance of its corresponding layers. So this is something which we do accurately and consistently. And in order to do this, the first step is temperature measurement. Specifically, we need to understand the temperature of the semiconductor die. Excuse me, traditional measurement techniques involve using thermocouples and infrared cameras, which are almost available in every single lab. For measuring semiconductor components, at least measuring die temperatures, they are not that good. And the reason is you need actually direct access to the die to be able to do measurements, and you can't really do that with either of the methodologies. You would need to open up the package or drill a hole, which actually won't give you very accurate data. And again, besides capturing temperatures, the most important thing to do is understand the contribution of certain package layers. So you can see here a TO220 package, and basically the heat is generated in this really tiny couple of micron thick active area. And the heat spreads through the die attach into the die flag. That's the end of the package. Then we use the thermal interface material and the heat sink in a very, very simple case. So what we're trying to help it is to give an understanding of the thermal resistance and the thermal capacitance of these individual layers, and basically the contribution of these layers to the entire thermal budget. The way we do this is based on electrical temperature measurements. So we are actually following a set of JEDEC standards, JEDEC GSD 51-1, which start with an identification of a so-called temperature sensitive parameter. You see here two examples. There is a simple diode where the forward voltage at a steady current acts as a temperature sensitive voltage value. But the same is true for gate emitter voltage of a bipolar junction transistor. And of course, we have different ways of measuring IGBTs, MOSFETs, and even complex digital ICs like the one you see here. So having identified a temperature sensitive electrical parameter on our component, we need to calibrate it to turn the component into a sensor. And that's typically done by placing the component in a thermally changeable environment, like on a heat sink where we can change the temperature, or in a chamber. And as we change the ambient temperature, we record the corresponding voltage change at steady biasing. This will give us a relationship between the voltage and the temperature, essentially turning our semiconductor into the temperature sensor itself. This can be done with high accuracy and high resolution. You see the 0.01 degrees Celsius value for the resolution of our systems. To understand the RTH, so thermal resistance, thermal capacitance features of the system, we need to use probing functions. Typically, it's a power step. So to establish it, we are using heating current source most of the time, which can be turned on and off, creating the high and the low power. And when we go from high to low, systems capture the corresponding voltage response. With a negative TSP, you actually can capture a positive and increasing voltage curve, which is temperature related. Using the calibration curve and a bit of a processing, this can be turned into an actual thermal transient response of the component for that given power step. And basically using a so-called inverse convolution method, mathematical method, we can deduct which thermal capacitances and thermal resistances make up this thermal transient response. Plotting these capacitances, the sum of the capacitances as a function of the sum of the resistances, we can come up with the so-called structure function, which actually graphically describes the contribution of the individual layers to the thermal budget. So you can, for example, see the partial thermal resistance of the die attach, partial thermal resistance of the TIM2, the thermal capacitance and thermal resistance of the base plate or the die, giving you a really good understanding of what's going on with your component and its cooling conditions. What do we use to capture this? We have the so-called MICRET Rister equipment. There are multiple versions of this unit. What I'm on though is, in every case, the test setup is simple and easy. So those very simple electrical schematics you've seen can be realized by connecting electrical wires to the component. You will see some examples using the Toshiba MOSFETs, which Jurgis explained before me. The measurements are highly repeatable and reproducible. So no matter where, with which equipment you are trying to reproduce the test, in the same thermal boundary conditions, you exactly get the same results. And that allows structure functions and this entire technology to be used in a supply chain to communicate thermal information. We can do this for almost every type of semiconductor component. And one of the very important things is that it's done in a non-destructive way. So you do the test, get the data, and basically you can take the component and place it back to its application. Yet you get a clear insight into the thermal structure. To give you an example, which we did on one of the MOSFETs we bought just off the shelf, it's a TO220 package. You can see a cartoon of its layer structure here. And we captured its structure function after a thermal transient measurement. The only reason we dissected this component was for us to be able to measure the internal geometry of different layers. And for some of them, like the die attach, we couldn't really get the height, and with that we couldn't get the volume. Now, if we analyze our structure function, first we can understand which part of the structure function corresponds to which layer, starting from the die, where from the thermal capacitance and knowing it's a silicon die, we can actually capture the volume of the material, which actually equals to the calculated volume here. And for the die attach, basically, we can also capture the capacitance. And if we know the material, we can get back the volume or the height of that layer very nicely. So there is a really strong relationship between material features, geometry, and the parts of the structure function. How do we use this in real life before I go to the two application examples? Well, you can use this for measuring either package standard metrics like junction to case, junction to solder pad, or junction to ambient, or simply the in situ thermal performance of a board or a component. You can also use this for reliability testing. So if you expose a component to reliability tests, could be power cycling, which we can actually do for you, or it could be something done in the chamber like thermal shock, high temperature storage, thermal cycling. If the component or any of the layers in the component degrades, then the structure functions would actually indicate that. And simply looking at the structure functions, you can understand the amount of the degradation and also the location of the degradation, giving you very valuable reliability information. You can also use this in production or actually checking incoming components, because simply looking at the die attach layer, you don't need a long measurement. You can do it in less than a second very easily. And it helps, or it enables the technology to be compatible with production lines. Excuse me. And then finally, you can also use this for modeling. I will show this in details at the end. Test can serve as an input for 3D CFD simulation studies. And using test input, we can make sure that our model is created perfectly. I'll elaborate this at the very end. So let me start with a use case, measurement use case, where we are going to use Toshiba test board and some Laird samples. And even though Jim has done a really nice job explaining what TIMs are used for, and most of you already know, I just wanted to share this brief simulation study. I think it's very nice one I took from my colleagues in the flow term domain. Basically, what you see, two realistic surfaces connected to each other. And if you have no TIM, you have all these air gaps with very low thermal conductivity. If we add TIM, it's not an additional thermal resistance in the heat flow path, because what happens without the TIM, the area of the heat transfer shrinks. So all the heat flux vectors in the simulation, they can actually cross the two boundaries at a very, very limited area. if you use this theme, which we simulated at 5 watt per meter Kelvin, fill in the gaps, the area heavily increases, and that gives us a 33% reduction in the overall thermal resistance, and also making our junction temperature significantly cooler. So how does this work in the real life? This is the very same board Jürgis introduced before me. So it's a test board aimed at motor drive and control for handheld power tool applications. The components used, they are dual side cooled Toshiba MOSFETs. On one side, they are soldered on the board and cooled towards the PCB. And on the other side, well, either we won't cool them, we'll show that case, or we will add thermal interface materials provided by Laird on the top of them and cool them through a heatsink. We use gap fillers, adhesives, and phase change materials from Laird for this purpose. So here is a quick cutout from the datasheet of the MOSFETs. The way they were measured, we used the reverse body diode for the measurement. We closed down the transistor with a gate voltage. And here is the sensor current or the measurement current creating the TSP. And this is the driving current source creating the change in the power step. For sensing, we use 200 milliamps, and for heating, and I will explain what these materials are immediately, but depending on the material type, we could have 10 to 20 amp heating current. We wanted to make sure that the junction temperature stays in average at 80 degrees, but definitely doesn't exceed 100. We could only go to 2 amps when there was no heat sink. So there's a big change here already, and you'll see it in some details why this is such. Not having any heat sink, the heating time was 3600 seconds, which we could shrink down for a steady state to steady state measurement to 240 seconds in all other cases. To better imagine the test setup, so here is the Toshiba board, and the thicker wires, they were used to provide the heating current, so to create a power step. And the thinner blue wires, they were used for gate voltage and also the sensing connections. In some cases, for some of those thin materials, which are not meant to be electrical insulators, we added a 1 mil thick Kapton insulation layer just to avoid short circuit. This was again optional depending on what type of material was used. Then we applied the TIM basically on the board and connect the board through the TIM to a liquid cooled heatsink. In each case, we applied 30 psi pressure, basically bringing down the materials to the minimum BLT. So I'm going to go step by step and explain what the materials are, but what you can see, all these colorful curves in the bottom lower than 10 Kelvin per watts, they were the cases when TIM was used. And the red curve indicates the case when we used only air cooling on one side and PCB cooling on the other side. At shorter times, it doesn't matter, but as the time passes, the thermal resistance difference gets extremely high. You see, we are over 50 Kelvin per watts here, and all the other cases are below 10 or even below 5. So how does this step? And how will you choose your teams, basically? First, we started with high performance PCMs, and as Jim explained, these are the materials which are used for the most critical components thermally. So the hottest components or which have the highest power densities, you can get them down to a thin bond line thickness, and you can see here all the applications where they are really excelling. We measured two of these materials, TPCM 7400 and 5400. They are both phase change materials. The only difference between them really is the back thermal conductivity. The 7400 being a bit more conductive. Sorry, I'm hearing some background noise. Thank you. So you see the two structure functions corresponding to the setup. The black and the gray show the two materials, and they are actually really good for the overall RTJA. You can see that at the end of the curve. And for better comparison for the other materials, we drew a line here. And this capacitance value 0.1 joule per Kelvin, which shows right when the heat gets out of the component. So these are the values here, TPCM being slightly less resistive as it's expected. And again, when would you use these kind of themes for the most critical applications? And one of the benefits of them is that they soften and flow at the transition temperatures, and this way they fill in the tiny gaps on the surfaces, minimizing the interfacial thermal resistance. And they have very good, very low pump out capability as well. So they are very reliable. And you may also want to choose based on how you can actually manufacture your parts. You can buy these in cut parts in strips and rolls and then fit them to the purpose. The next family of materials we tested was the two-part liquid gap fillers. Again, Jim explained detailedly what these are for, but when we just revisit this, they are mostly appreciated by the automotive industry because they can replace air for larger gaps, and they require low assembly force. So when you're dealing with materials where this is important, you can definitely rely on these kind of themes. How do they compare? Well, we tested two of them, CR607 and CR350. Again, there was a slight difference between the thermal conductivity coefficients, CR607 being more conductive, and this is reflected in the data. For the overall RTJA, they are still very close to the phase change materials, but again, they serve a different purpose. So applications are more about meeting stringent shock and vibration requirements for automotive or transportation industry, filling larger gap tolerances, low stress during assembly, and basically they are supplied in a one-to-one mixture, so you can use them with a variety of dispensing equipment. Finally, what we tested was gap fillers. Here you can choose materials in a wide range of conductivity coefficients, 1 to 8 watt per meter Kelvin bulk, a wide range of thicknesses depending on the application. And these materials from Laird, they are low deflection, so also you can achieve a low mounting pressure when you create your assemblies. The way they compared, we tested two materials, HD720 and 320. They showed slightly higher thermal resistance values, both at our reference point and in the ambient. Still really good, so below even 8 Kelvin per watt junction to ambient. And just to put this into perspective, I'm going to compare it to air immediately. For applications, one of the good things is you can go all the way from basic consumer applications through automotive and even aerospace and defense. High deflection, low mechanical stress on the component, and it's very easy to deal with these kind of materials. You can actually cut them to the shape and size you're needing to fill. So putting this into perspective, comparing it to air, you see for the air gap, the overall thermal resistance is beyond 50 Kelvin per watts. So the curves which I have shown shrink significantly with respect to an air gap. And why is this important? It is an overview table. First of all, the current consumption, how much current can you use to operate the MOSFETs, heavily depends on this. Here are the maximum junction temperatures. As I said, we try to keep them below 100 degrees Celsius, in average roughly at 80. And we could go all the way up to 20 or 15 amps with most of the materials, but only 2.2 amps with air. And yet the temperature was over 90 degrees. And the way this reflects to the power dissipation on the component, we could do 14 watts with the best-in-class material versus only 1.2 watts when no TIM was used. So it's a massive change, and it's very important to do the thermal design properly. I'd like to give the word back to Jim for one slide where he'll talk about automated TIM solutions Laird can offer.
Thanks, Andreas. Yes, on top of providing, TIM solutions, we like to take it one step further and provide our customers with solutions to applying these materials. And here's a video that we're going to show now of some of those materials being applied, both pads and dispensables. So this is a video of dispensing a one part. I believe this is our T-Putty 607. And we can help you select all of the speeds and feeds and cartridge sizes and help you select a vendor to use. We have relationships with all the key dispensing vendors. Again, showing this being applied on multiple components on the circuit board. The next video is of our TIM print. This is a system for applying phase change materials. The materials here are being cut actually and applied through the polyester liner, which is kind of the trick to this system. It keeps the integrity of the roll. We can apply the same pressure that's at the same temperature and get a really good placement of the parts. And finally is the TIM pick. This is a system for cutting and placing gap fillers. Again, this can be used with pretty much any standard robotic system you might find in a CM's facility. We would just apply, provide the head, which would go on the device, which would be customized for cutting and placing the specific material. So let us know if you would like us to help you with any type of automation system for applying any of our TIM materials. Thanks, and back to you, Andreas.
Thank you very much, Jim. So one of the reasons, and we put this automation part to this section of the presentation is I'd like to move on towards quality. So how can we use these technologies for quality testing? And from the quality perspective, thermal interface materials also play a very important role. Here's an example. We have two cartoons. One is a package with no issues at all. The other package has some air gaps in its Team 1, so die-attach material. And as you could see in the animation I showed earlier, air gaps would increase the thermal resistance significantly, reducing the quality and the reliability of the entire assembly. This is still true for die-attach and also for maybe not correctly placed thermal interface 2 materials. And when it comes to automation, it makes a lot of sense actually testing the quality and reliability of these interfaces. And I also would like to show a video. This is one of our concept systems, actually the one on the left. This is being rolled out to the market right now in a couple of weeks. It's our quality test system, and the robot which you see is a demonstrative test handler. What we do is we actually picked components. These are TO247 package transistors. The robot is picking them up, moving them to a measurement station. It's synchronized to the tester. So now once it connects, we take a quick transient measurement. And based on the measurement, we make a decision and put the component into a bin, depending on its thermal quality. To do this, we can actually select all kinds of devices I've shown earlier: diodes, MOSFETs, IGBTs, and on the MOSFET side, it can be silicon or silicon carbide. We set up the measurement parameters, and have the machine take a reference measurement. So we select what we like to call a golden reference. It's a device which doesn't have any errors. And then around this golden reference device, we create bands. So when we make a measurement on an unknown device, the closer the data is to the golden reference, the higher the quality. The farther it is, the lower the quality, or maybe the component just goes to a different bin. And when you start the measurement, everything is automated. So we have a gravity feeder here, pick up the component, test it, make a quick decision, and go again and again until all the components are measured. What you see here seems to be a slow process, but the bottleneck really is the robot we used for the demonstration. The measurement itself can take place as quick as like 0.1 seconds. And with a proper handler, we can actually do full factory automation. Let me show you a case study. So with the same robot, we actually measure 70 Toshiba TO247 MOSFETs. You can see the part number here. These were not provided by Toshiba. We purchased them by a distributor, so they are in the market. We just did a sampling. The electric schematic of the component is here. It's recommended for switching power supply applications by Toshiba. And the reported RTHJC is 0.347 Kelvin per watts. So what we did was measured 70 of these units. You see, these are structure functions I zoomed in for better visibility. This is right after the die attach layer. And these 70 functions, they overlap very, very nicely. The scatter is 0.016 Kelvin per watts. This is the maximum scatter, which is less than plus minus 2.5% of the reported RTHJC, which is actually considered to be excellent. Typically, most manufacturers, and I'm not talking on behalf of Toshiba, that this is the common situation. There is a variation of these values. This is a very low variation off the shelf for off-the-shelf components. So if you do this kind of analysis, you can actually make sure what you use is reliable. You're not building a component into your system which might have issues. And actually, this is a very good way to filter potential counterfeit components, because definitely they will have a different thermal signature. And finally, I have 2 more slides on model calibration, where the idea is, if you create a simulation model, you want to make sure that it's accurate and you're getting the right simulation results for the right reasons. If you see these two simple images, both of them have 10 Kelvin per watt overall thermal resistance, but as you see, the geometries are different, and you can do this by playing around with the conductivity values. So knowing the geometry and making measurements, you can make sure that the models will be perfect. The workflow is simple. Here is the test board, which we measured earlier. We take a structure function, and then we create a simulation equivalent of the board. There are 2 tools we recommend. One is SimCenter Floater, and the other is SimCenter Flow EFD, which can do this. They both can take the measurement-based input, and they can run a simulation under the same boundary conditions. So same power step, same ambient temperature, same heat source. And what the tool does, it compares the structure functions corresponding to the uncalibrated and the calibrated model, and iterates until the 2 structure functions overlap. Why is this important to go from uncalibrated to calibrated? First of all, you'll get the maximum temperatures right. Also, you will get the temperature fields right. It's very important when it comes to structural simulation like stress. And finally, you can be sure, if you have this done for the full junction to ambient path, your model will be give the right results also for a complex transient simulation like a mission profile based simulation. So if you do this, you'll have what we call in Siemens a digital twin of your component. you will be able to use it in the supply chain, so you can actually provide accurate thermal models to your customers. And in case you see deviations, either in simulation or test, you can use these models to uncover the reason of those deviations. This is where I would like to finish my part of the presentation, and back to Mark for a summary. Thank you.
Thanks, Andrus. Appreciate it. Thank you, Jurgis and Jim as well. We're on to the last slide. Just a summary, and then we'll get into the questions and answers. And thanks for attending, everybody. But we've gone through and give you an overview of the power electronics. Thermal management is important for high reliability of your products. We've shown you how to leverage new power device and packaging technologies and guidelines. We've helped explore and show you how thermal interface materials perform fully to enhance your design. We've also given you an overview of how to leverage accurate thermal tests and simulation to have the highest confidence in your design. And finally, the last part of this, we showed you how you can ensure thermal quality in the manufacturing from device to package integration in your end product, and ensure that you're not going to have any failures of the thermal stack and system. So I think we've covered off what we wanted. We hope you've enjoyed it. We'd like to thank everybody for attending. And now Peter's going to go through and ask some of the questions. Peter, are there any questions?
Thanks, Mike. Yep, there's a couple of questions coming in. We'll start with one for Andrus. Types of, can you test compound semiconductor devices, SiC GaN, with this technology?
Thank you, Peter, for this question. Yes, the answer is yes. So compound semiconductors are becoming very important, as you could see it in both Jim's and Jurgis's presentations, and we are prepared for those. We have by now tons of experience with silicon carbide components. This is something we do on a daily basis. And gallium nitride, as the technology is becoming more and more mature, we are trying to keep up. So we put a lot of effort into measuring them, and we have some really promising results.
Thank you, Andrus. We'll move on to a question for Laird. Does Laird help with identifying the best type of dispensing equipment for the application?
Sure, we sure do. We have relationships with all of the key dispensing equipment manufacturers. So we can definitely point customers in the right direction.
Okay, thank you, John. One other question for Laird. Regarding the GOF product, you talked about the high thermal conductivity, XY. What about the Z and the ability to move heat in and out of the plane, on the Z plane?
So the thermal conductivity in the XY on a silicon or a synthetic graphite, you know, it pushes 1,000, which is really, really high. And the Z conductivity is in the 10 range. So there's a big difference between the Z plane and the XY plane. Graphite is, you know, a really good heat spreader. And so what we're trying to do in large gap applications is move the heat kind of around the outside using that high thermal conductivity in the XY. You know, using silicon, or not, I keep on saying silicon, synthetic graphite as just a TIM material, even though it does have a high thermal conductivity of 10, it's a relatively hard material, and therefore it does not handle or reduce the contact resistance between the interface surface and the graphite itself. It works, and again, when you're looking at large gaps, like we're talking about using the GOF material, that resistance is relatively small compared to the resistance of the overall interface gap.
Thank you, John. Question for Andrus. When are you going to have the new 3-stir system, which is able to do the measurement of cycle power? Basically, I'd like to see the temperature response of the device during the operations of power cycling.
Thank you for this question. Actually, when I showed the four uses of structure functions, reliability was one of them, and I think the question is related to that. We do have a system, actually a set of systems, which we call the power cycling tester, which can exactly do the same. So it can turn on and off the heating power in a cyclical way. And for each cycle, we can measure the temperature change, so the delta T and the maximum TJ. And time to time, as you keep on doing the cycling, we can capture structure functions to make sure that nothing happened to the structure. If the structure is degraded, we can capture that. So we do have this system available, and I'm very happy to talk about this in details to the person who asked the question.
Thanks, Andres. That was from Eric. Another question for Andres from Sanjay. Is there some literature describing the working of the three-stir tester, which explains thermal capacitance versus the thermal resistance curve presented?
Absolutely, we do have a number of white papers and technical papers on structure functions. So I'd be very happy to provide a couple of links and titles which can be checked in this domain.
Okay, that was from Sanjay. Question from Jurgis. Does your DMOS have an automotive version, automotive qual?
Can you repeat, please? I don't see it in the written questions. Which one?
Your DMOS automotive qual, does it have an automotive qual version?
So we have automotive qualification for low voltage FETs, so up to 100 volt. And for high voltage MOSFETs, unfortunately, at this moment, we do not have automotive grade. So again, low voltage FETs, we do have.
And one other question that came through from Tushar. Actually, Tushar, we'll reach out to you individually for FlowTherm and Flow EFD. And I believe the last question here is what kind of test handlers, this is for Andres, I believe, what kind of test handlers is your quality tester compatible with? Do you provide test handlers or do you integrate the existing handling system that your customers have?
So when it comes to test handlers, the system we are basically rolling out right now is just the electronics part, so the measurement part. It doesn't contain a test handler. So we expect our customers having a handler and we're integrating to it. This can be a wide variety of handlers, so for lower scale production to more advanced factories. However, in some cases, if our customers are interested in us providing something similar to the robotic arm I have shown, but maybe more fast, then that is also something we can arrange and help with. But I think my answer is we are more integrating to existing handlers.
Thank you, Andres. Mike, that's it for the open questions. I believe a number of them have been answered already in the chat window.
Thanks, Peter. Appreciate it. I'd like to thank everybody for attending again. We'd like to thank everybody. Have a great day and stay safe. Thank you very much.